So I guess we have another Blackboard day today. We're going to talk about the same type of hypothesis testing that we started talking about yesterday. This time we're going to talk about the cases where we do not know our population standard deviation, but we do know our sample standard deviation. Much like the confidence interval, we'll be using the t-statistic instead of the z-statistic for these cases. This is a formula. It looks a lot like the z-statistic formula. We're just substituting the t for the z and the s for the standard deviation of the population. We're going to be looking at the t-chart a little differently in a couple of slides. We'll look at how we find what we're looking for in the significance level with our t-chart for this particular type of problem. But other than that, straightforward. This is going to be the math portion to find our value, to compare it to the significance level value and see if we reject or not reject, just like we were talking about yesterday. So here is our first example. I think this one has some data with it that it asks you to find the standard deviation and the n from the data rather than it being given in the problem. But we have a mean cost to process a claim of $60. And an industry comparison showed that this amount to be larger than most other insurance companies. So we're going to have to do this comparison to see which way it goes. To evaluate the most effective cost-cutting measures, a supervisor is selecting 26 claims to see where they fall in with the normal mean. At the 0.01 significance level, is it reasonable to claim? Is it reasonable a claim is now less than $60? So think about how we're going to write this hypothesis. That's the first thing we need to do. Of course, 60 is going to be what our number is for both of our HO and our H1. And so we just have to think of the little symbols, the greater than, less than, those kind of symbols. So looking at this, we're actually wanting to write our alternate hypothesis first. And the alternate hypothesis would be about the claim being now less than 60. So our alternate hypothesis is going to look like our mu is less than 60. It's going to say exactly what the problem states. And so our null hypothesis will be written as mu is greater than or equal to 60. So it's always easier to write that alternate hypothesis first, I think. Our significance level is given, and we're going to use the t-statistic. Now, I don't know if you quickly, while I was talking, found the standard deviation for this and counted up how many of them there were, but there are 26 of them. So we can go on to the next part. We're going to look at our t-chart again. If you have one in your book, pull it up because this one isn't very easy to read, I don't think. But we're again going to look at our degrees of freedom. We're going to look at our degrees of freedom on this side. It is always n minus 1. So the sample size was 26. Our degrees of freedom will be 25. And then we're going to come over to the chart. Now, why this column? We are performing a one-tailed test. Since it's a greater than or less than problem, we have all of our information in one end or the other. The equals problems are the two-tailed test. So we're finding a one-tailed test for 0.01 significance level right here. So that's why we look at this column right here. There was a two-tailed test and we were using that same significance level. It would actually be over here in this column. So make sure you find the right column and we come down, make it level with our 25, which is our degrees of freedom, and we get 2.485. Now remember what this is. We're in the negative territory, right? So it's actually going to be a negative 2.485 because our problem was written that we were trying to talk about less than 60, right, for our alternate hypothesis. So if we get a number that's down here in this little shaded area, then we will reject our hypothesis. So when we do the number thing, we actually crunch some numbers here, and it's 10.04. If you did the standard deviation of that data, that's where you get that. It is divided by the square root of n, not n minus 1, but just n. And here we have our x bar and our mu. So when we put these numbers together, we get a minus 1.818. So we are in this half down here, this area. But this number is not all the way down here, right? We're looking for it to be far down on the number line, less than as we go that direction. We are looking for the number to be less than negative 2.485, and this is not. So what does that mean? Well, it means that we do not reject, right? We do not reject our null hypothesis. We have not demonstrated that these cost-cutting measures have reduced the mean cost per claim to less than $60. So that's how we answer that question. Remember, we aren't proving H naught or the null hypothesis. We are just saying do not reject. Okay, here's one more. Let's see how we set this one up. Here we have a current rate for producing some fuses is $250 per hour. They buy a new machine and install it, and the person that sold them the machine says that this is going to raise their production rates. A sample of 10 randomly selected hours from the last month revealed that the mean hourly production on the new machine is 256 units. Sounds like it works. Does it really? Let's find out. The sample standard deviation is 6 per hour. So they only took the standard deviation on those select sample. So it isn't a population, so we're going to use the t statistic. At the 0.05 significance level, can they conclude that this machine is faster? So what parts of this do we need? We need the significance level. We need to know if it's a t or a z. We need to know our standard deviation for the sample or population, and our n, the number that we sampled, plus our mean. We have that information, so we can go ahead and write our hypothesis. Again, I would start with the alternate hypothesis, which would be, is my mu greater than 250? Am I producing more than 250? And then we would write the null hypothesis, which would be less than or equal to. We have our significance level, and we're using the t distribution because the population standard deviation is not known, and my sample size is less than 30, which means it's going to be on my chart. Otherwise, I would have to go down to infinity, which is the same thing as my z. So here's the math that we're going to do. We look in our chart at 9 degrees of freedom, and we then come up with, that's where we get this number right here. They didn't draw a picture for us this time. But this right here is when I look at 9 degrees of freedom, and my significance level, let's go back and look at our significance level, is 0.05, and it is 1 tail. Okay, so that's where I get that t. I'm going to reject if t is greater than 1.833. Do the math right here, and I end up with 3.162. Wow, that's a lot greater. So we reject. We reject the null hypothesis. We have changed the mean by using this new machine. We have increased our production. The book goes on in this chapter to talk about the p-value, or the probability factor that comes in with this hypothesis testing. Some very interesting stuff. But I think if we can understand these two concepts while we're having these snow days, that will be great. And when we get back together, we will just make sure that we do understand those concepts. I'm going to include a question in the discussion board to have you actually write a hypothesis question so that we can make sure that we have that well in hand. And hopefully we will see each other soon. Thanks.